Intersection of planes. In the following system of equations, k is a real number. Minus 2x plus y plus z equals to k plus 1, kx plus z equals to 0, and y plus kz is 0. For what values of k does the system have exactly one solution? That's what you have to figure out. For what values of k will this system have exactly one solution? Now what does that mean? It means that if we do the reduction of the matrix, then what kind of situation should we land into? Let's look into that first, right? So I think, let me put it like this for you. The matrix should look like this. So what we have is, one solution means we should have 0 here, and something here, so that z equals to a number here. Do you understand? So that means a point, correct? And so this is what we're looking for. And then we can solve for y. Once we know the z, we can solve for y. So that means we have something here, we have something here, right? And 0 here. So from here we get z equals to a point value. Then y plus z equals to point value, so we can solve for y. And then we should have like this to solve for x. So in this kind of a situation, we can get point as the intersection of three planes, or the system of equations as shown here, right? So that is what we're trying to get into. So what we will do is we'll start with the augmented matrix from the given equations and do elementary operations on the row to reduce it in this form, and then figure out the value of k. This should not be 0. That's kind of critical for us. If this is 0, if it comes to this becomes 0, and this is also 0, then it's a line. If this is 0 and this is something else, then they don't intersect, correct? So those are the different scenarios which we can look into. So what we are basically now looking into, because we need, for what values of k does the system have exactly one solution? For one solution, this should not be 0 here, right? So let's now write down the augmented matrix and then see how to reduce it into that stage. So here, minus 2, 1, 1, and then here we have k plus 1. Correct? Now x is k for us, y is 0 for us, and z is 1, and this is 0. Right? Y, that means x, coefficient of x is 0, right? Coefficient of y is 1, and coefficient of z is k, and here we get. So that's our augmented matrix. In augmented matrix, what we are doing here, we are only writing coefficients of our variables on the left side of this line, and those values on the right side of the line. So once we do that, we have our augmented matrix. Now from here, we'll try to reduce. We already have a 0 here. We got this 0 already. We want to make this as 0. So to make this 0, what should we do? We should multiply this by k, so we get minus 2k, and this by 2 to get this as 0, right? And then add them up. So that's what we will do. So what we will do here is we'll multiply row 1 by k. So let me first draw this matrix, and then so first row is going to remain as such. It's a good practice to copy the first row as such. 2, 1, 1. We kind of get a framework also to fill in other values. And in the second row, we need 0 here, right? So we'll multiply row 1 by k. So we say k times r1, and then we will add 2 times row 2. 2 times row 2. Is it okay? So once we do that, then we get our second row, correct? So which will be 0k, k plus 2. And when you multiply this by k, it becomes k square, correct? So don't forget that. So it's k square plus k, right? 0 is there, so k square plus k. So that is how we get our second row, right? And we'll just copy the third row as such for the time being. Is it okay? Now what do we need is, we need 0 here, correct? And for that, we can just subtract this from here and then get 0, correct? So that's what we will do now. So let me just copy the first row as such and then move on as we did. Write the conditions. So we get -2, 1, 1 in k plus 1. So now we want 0 here, so we'll multiply, or we can use R2 and R3 also, because, well, to get this 0, what we will do is we'll do minus k we can multiply this by minus k and then add this up. That also we can do. So we'll do minus k times R3 plus R2. So basically what we are doing is we are multiplying this by minus k, right? And then adding this with R2. So if I multiply this by minus k and add this up, then minus k plus k will be 0, right? So we are not doing any operation with the second row, so let me copy the second row as such. And when I multiply R3 by k, so and then minus k, and then add this up, I get 0 here, right? And this place I get k square b. So let me first write this, because minus so R2 is k plus 2 and this is minus k, so minus k times k will be minus k square. Less space for me. And 0 times anything is 0, but I have to add this k square plus k, so I get k square plus k here. So that's what we get in our third row. Now as you can see, the condition for them to intersect in the point is that k plus 2 minus k square should not be 0, right? So we'll put that condition and then solve. So for one solution, that means just a point of intersection is 1 point. This should not be 0, correct? So we have the condition as k minus 2 minus k square is not equal to 0. That is the condition, right? So we can factor this out. So this gives us k minus 2 times k plus 1 is not equal to 0. Or it says that k is not equal to 2 or k is not equal to minus 1. So that is the solution. So when k is not equal to 2 or k is not equal to minus 1, then this cannot be 0, right? Because this is 0 only for these two values of k. Okay? So for all other k's, we have one solution, correct? So we say k belongs to real numbers. So the solution is that k belongs to real numbers where k is not equal to 2 and k is not equal to minus 1. Okay? So that's how we derive at our solution, right?